All right, hi everybody. Sorry for this morning. I really wanted to be there. Hope you weren't too upset about getting out early today. But nonetheless, we do have some important things to cover, so I'm feeling momentarily okay to go ahead and make this video. So let's get to it. So we left off on Wednesday talking about um, limits. And so I want to pick up where we left off. Um, if you recall, we were looking at the function a of x equals x squared and determined that the average rate of change over every delta x interval is given by um, this quotient, okay? And so this quotient right here, so we look at the changes in accumulation relative to changes in input, okay? And that gives us our average rate of change. Now, then we said if we imagine delta x getting really small, then the quotient is essentially equal to 2x. So let's remind ourselves what this essentially equal means. Okay, so when I write this equal symbol with the dot above it, that means that the values of the two expressions are essentially equal for exceedingly small values of delta x. In other words, both expressions produce essentially the same number for sufficiently small values of x. And another way of saying that is for every x value, there is no number between this quotient expression and 2x when we let delta x get crazy tiny, okay? So let's analyze this third statement again really fast. So what does it mean to say that there's no number in between these two expressions if we let delta x get really small? That means if I choose a value for x, and I try to think of a number that's in between the values of these two expressions. So once I've picked, so we did this on Wednesday for values of x equal to 5, right? So we plugged in a value for x equal to 5, and we got that this expression is 10. And for different values of delta x, we got different numerical values of this expression. Okay, but then I picked a number in between the value of the quotient and then the value of 2x, and I said, oh wait, I can pick an even smaller value of delta x that will make it so that the number I was thinking of is not in between the quotient and 2x. Okay, and so that's how we're thinking about this idea of there being no number in between these two expressions as we let delta x get really sufficiently small. Okay. And so then the way that we formalize that idea, or the way that most textbooks commonly formalize it, is to write this type of expression. Okay, so let's take a look at this type of notation really fast. So conventionally, people will say or use h instead of delta x, and so the notation that will be used in your textbook to talk about this idea is to say the limit as h goes to 0 of x plus h squared minus x squared over h equals 2x. Okay, and so this is the notation that's most conventionally used in most calculus classes and things like that. But what I want you guys to keep in mind is, what does this actually mean? Okay, and so that's why we've talked about this idea of essentially equal, because when we see this in your textbook and in your homework, I want you to think this. okay? So when you see an expression about a limit as something happens, so in particular the limit as h goes to 0 if some expression equals some other expression, that means those two expressions are essentially equal. Okay, so we say the limit of this quotient as h approaches 0 is 2x, meaning that these two expressions, the quotient and the expression 2x, are essentially equal for very small values of h, and for each x, there is no number in between these two expressions. Okay? So, what have we done? We have, in fact, taken any exact accumulation function, and we've found its exact rate of change function, and we did that again by considering the expression for the average rate of change over delta x intervals and letting delta x get crazy tiny, okay? And we call the resulting essentially equal expression the derivative of g, okay? So time to put on your party hats, people, because we did it, okay? So we have the derivative, or the notion of the derivative. And so in our example so far, we have that 2x is the exact rate of change function for the area function f of x equals x squared, and thus 2x is the derivative of the function f. So two quick things to remind you of when we look at this, because I don't want us to forget everything that we worked so hard for. So 2x is the exact rate of change function for the area function f of x equals x squared. So when I look at this, and when you look at this, hopefully you remember, okay, so this expression is the rule for a function. So I'm going to introduce some notation, okay, to really keep us on track with that, for this given exact accumulation function, okay? So when we talk about a derivative of a function, we're also getting a function, okay? Okay, so let's talk about the notation. Okay. So let f be any function. We're going to use the notation r subscript of f, subscript f of x, to denote f's exact rate of change function, which is the function whose values give the rate of change of f with respect to x. Okay? And so that is to say that we're going to let r sub f of x equal the limit of the quotient that we talked about representing the average rate of change over small intervals of size h. So once again, this quotient gives you the average rate of change of your function over small intervals of h, and then we're letting those intervals get teeny tiny to make this approximate average rate of change, or the average rate of change, which is an approximation to our function f, actually be essentially equal to the exact rate of change function, okay? So then when we read this notation, so don't do what I just did on the last slide. I did it because I hadn't introduced this slide yet, okay? But the way that we're going to read this notation is to say the rate of change of the function f with respect to its input x, okay? So that's how we read this notation. So when I look at this function, this is the rate of change of the function f, okay? And we just saw that it's defined as the limit as h goes to 0 of f of x plus h minus f of x over h for a given function f, right? So this function here lines up with this function here, okay? Now, I've highlighted it in red and said, let's call this version, or this expression, this definition, if you will, the open form. Now, what we're going to discover really soon is that you can oftentimes simplify this into something really nice and compact, right? Because we're used to, if my function f of x was x squared, it would be really nice if I didn't have to write that the rate of change is the limit as h goes to 0 of x plus h quantity squared minus x squared all over h. So what I'm hoping for is a nicer, compact form of this rate of change of f function, okay? And so what we're going to see is that we can often simplify this open form expression and obtain a closed form for the derivative function, okay? So let's see how that works, okay? So for this function, g of x equals 3x squared, okay, I'm going to write both the open form and a closed form for the corresponding exact rate of change function, okay? So now would be a really good time to pause the video and ask yourself if you can write down the open form for the exact rate of change function corresponding to g of x. So what I'm wanting you to do is pause the video and write down the expression for this function, okay? Now I'm just going to keep talking because you can pause the video. So what this will end up looking like is, by definition, okay, this is the generic form of the definition where now I'm looking at the rate of change of g. So I've got g's here, right, because that's the function that I'm looking for its rate of change function, okay? And now when I actually use the fact that I have the rule for g of x, then I can actually figure out what is g of x plus h. Well, that's 3 times the quantity x plus h squared. G of x is 3x squared. So this is the open form for the rate of change function for the accumulation function g, okay? Now, if I wanted to simplify that and achieve a closed form version, then what I can do is expand out this expression, okay? And so you had a little bit of practice with this in your graphing calculator homework assignment, so you can type in this kind of thing and ask graphing calculator to do the work for you. But I'll go ahead and do it by hand for now. So if I expand this numerator out, I get 3 times x squared plus 2xh plus h squared minus 3x squared all over h. And now I can distribute the 3 to get this expression in the numerator. And then I can observe that this term and this term subtract off. So then I'm left with these two terms in the numerator, okay, and they both have an h. So I'm going to factor out an h, and I get 6x plus 3h all over h. And now h divided by h reduces to 1, so I just get 6x plus 3h, okay? And so then notice, so I have done this without worrying about the limit over here, right? And so now what I want to do to achieve my closed form is to say, okay, well, so I've simplified the quotient. We call this a difference quotient, okay? So I've simplified the difference quotient to look like 6x plus 3h, but now I want to ask, what is this expression essentially equal to, okay? So meaning when I let h get crazy tiny, okay, what happens to this expression? And that's when we see that this expression becomes essentially equal to, well, sorry, let me back up. So let me not write it that way. Let me say that this expression is essentially equal to 6x, right? Because when I let h get very small, this left-hand expression becomes essentially equal to just 6x, which allows me to say that the rate of change of the function g with respect to x is just 6x, okay? And so this is the closed form of the exact rate of change function corresponding to this function g of x, okay? So, great. There it is. So you might be asking yourself right now, why bother with this open form version, right? If we have such a neat, compact, closed form version. So let's quickly discuss the advantages of each, okay? And you might, again, pause the video and try to brainstorm yourself what might be the advantage or disadvantage of each of these forms, okay? So certainly the advantage of the open form version is that it reveals the process, right? So when I look at this expression, I can really break down that this piece of it is looking at the average rate of change of the function over intervals of size h, right? And then I'm letting those intervals get really small, and so these rates of change become really good approximations to what the actual rate of change is. And so when we have this open form expression, it reveals to us the process of how this whole thing works. Okay. Well, when we have the closed form version, okay, we don't see the process anymore. So then you might ask yourself, well, what's the good of it? Well, the good in having a closed form is that it's a nice, compact little, equation that I can easily say, okay, well, I want to know what the rate of change of the function g is with respect to x when, say, x is 3. Okay, well then I can do that really fast just by using this function, right? And I instantly, I can use all of the power of having a function where I can just plug in an input and get an output in a really quick fashion, okay? Now that's not to say I just realized that my last statement might be confused a little bit. This is still a function, and you can still do what I just did here over here. It just will take a little longer. Okay, so this is still a function, this is still a function. They are in fact the same function, which is why I can use the same label for both of them. Okay, it's just that one way of writing it, the open form, shows us the process behind the function, and the other form just helps us get to answers really quickly. Okay? All right, so since we do have a lot of other ideas that we want to be able to grapple with and problems that we want to be able to solve and do them in a timely fashion, there are a lot of rules for finding closed form derivatives. Okay, so let's start to get on this journey of figuring out what all of these rules are. Okay, so once again, we're shifting into learning some of the rules that are going to allow us to quickly determine closed form rate of change functions, i.e. derivatives. Okay, so all of these rules are derived from the open form. So take a second, make sure you can fill out what this should equal. Pause your video, fill in the blank, and come back and check your answer, which should look like this. Okay, so once again, we took all this time to build up this idea for a reason, right? It's important. So this is the open form for finding the exact rate of change function for any function f. So everything we're doing can be established by thinking about this equation and just applying it to different functions f. Okay? So the generalized open form above is also called the definition of the derivative. So this is, when I used to teach calculus the traditional way, this was the big deal thing that we got to in about week 3, but nobody understood what the heck it meant as much as I tried. So congratulations, guys. I hope that this means something to you. So we're here. So let's talk about some of these rules. Okay. So the first function that I want to look at is the function f of x equals x to the n. Okay. So in order to find the exact rate of change function for this function f, I'm going to remind us of a few things. Okay, so if n were a 2, then the tricky part about figuring out what f of x plus h is that you have to do x plus h to the nth power. Okay, why am I asking what f of x plus h would look like? Well, because I want the rate of change function, and remember that requires me to look at the limit as h goes to 0 of f of x plus h. So I need to know what that looks like, minus f of x all over h. Okay, so at some point when I'm trying to figure out what a simplified version of this looks like, I need to be able to handle what does f of x plus h look like. Well, that looks like this, right? But that's not going to be useful for simplifying this expression in the numerator. So let's see if we can figure out how to expand this right-hand side, x plus h to the n, in general. Okay, so x plus h squared looks like this. X plus h cubed looks like this. N to the 4th, n to the nth. Okay, and so the things to observe here are that you always, the first and last term are raised to the nth power. The powers of the x and the h in the middle terms add up to n, and then we get different coefficients along the way. Okay, but the thing to pay attention to is because of the structure that you get when you expand this out is that all of the terms after the first term have an h in them. Okay, so everything in this dot 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 has an h, and then everything at the end has an h. Okay, so that's just a reminder so that we can proceed. Okay, so what we're doing once again is we're finding a rule for the exact rate of change function when f of x equals x to the n, and what we're doing is going to work for any natural number n. Okay, so 1, 2, 3, 4, 5, 6, etc. Okay. And so remember that in order to find the exact rate of change function, we have to work with this expression. Now let me not say that those are equal because this is missing the limit. So let me just erase this for a second and just sort of remind ourselves that we need to work with this expression, this quotient, while we're trying to solve this. Okay, so this quotient with this as my function f looks like x plus h to the n minus x to the n over h. And so as we saw in the previous slide, when I expand out x plus h to the n, I get this very long sum of terms, okay, where we can notice that the x to the n's subtract off, and then I'm left with just all of this other junk, okay? But notice that all of this junk up here has an h in it. So what I can do is, in particular, focus on this first term divided by h, and notice that the h's reduce. So I get just n times x to the n minus 1, and then I kept the rest of this stuff as a fraction, okay, or quotient. And so each of these terms still have an h in them, so I can factor out the h and reduce with the h in the denominator. So I end up with something like this, where notice all of these terms still have an h in it, right? Because I was reducing things like h squared, h cubed, h to the fourth, all the way up to h to the n, and dividing by h. So I still end up with h's in each of these terms. And so when I let h go to 0, all of this stuff in parentheses goes to 0 with it, right? Because all of these terms are essentially becoming 0. Okay, so that makes this expression essentially equal to, right, this whole line is essentially equal to n times x to the n minus 1 for exceptionally small values of h. Okay, so that means that our rate of change function of f with respect to x is n times x to the n minus 1. Okay, and so we actually, we saw that with our area function, right? A of x equals x squared. So the rate of change of the function a with respect to x using this rule, this rule, okay, it says that I take the exponent, I bring it forward, and multiply by x to the n minus 1, okay, so just 2 times x. And this is the rule that we established for our rate of change function when this was our area function. Okay, so now that is our result. Let's look at another type of function. So this time, if we think about a constant function, once again, take a second, think to yourself, what does a constant function look like? Have you thought of it? Okay, good. So then, if we're thinking of this type of constant function as being an accumulation function, well, that means that it never accumulates anything, right? Because it's always the same value. There's never any changes in the output value of a constant function. So if there's never any changes in the value, what would the rate of change be? Okay, so hopefully you thought, or you paused to think, and you came up with 0. Right? If it's never accumulating anything, then there's no rate of change to model the rate at which things accumulate. Okay, so let's see if we can establish this mathematically. Okay, so let's take a constant function. That'll look like f of x equals some constant c. Then the rate of change of f with respect to x is this, the limit of this difference quotient, okay? But then f of x plus h, well, when I plug in x plus h as my input, my output is c. So this is c. And then f of x is c, right? So this whole thing is actually the same as the limit as h goes to 0 of c minus c over h. But c minus c is 0. And 0 divided by something that's not 0, right? Because we're imagining h is still some non-zero value that we're letting get really tiny, right? So that's what's happening. So when I divide 0 by something else, I get 0, okay? And 0 is always essentially equal to 0, okay? So this whole chain of deductions that I've made here is a mathematical proof. Holy cow. So we just proved that the exact rate of change function for the function f of x equals c is the function 0. Okay, so there it is. And you guys have now done 2 proofs in your Calculus 1 class. That's pretty cool. Okay. All right, so we've just established a rule for taking the derivative or finding the corresponding exact rate of change function for a constant function. But what happens if we're talking about a comparison between 2 functions? So let's for a moment sort of like switch gears to think about an actual situation. So at every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? So pause the video, take a second to think about it. And now that you've thought about it, let's talk about it. So hopefully the conclusion you were able to arrive at is that at every moment in time, John's speed is 5 times Mary's speed. Okay, so this, of course, comes from all of our conversations earlier in the semester about the relationship between speed, distance, and time. And so in particular, the statement of the problem was that John travels 5 times as far as Mary. So we could model that using functions. So if f of x is John's total distance after x hours, then and Mary's total distance after x hours is given by the function g of x, then this first statement can be modeled by saying f of x equals 5g of x. Okay, so this is the mathematical statement corresponding to the first sentence in the problem. Okay, and then by thinking about the relationship between distance, speed, and time that we established early in the semester, we were able to conclude that at every moment in time, John's speed is 5 times that of Mary's speed. Okay, well, remember, speed is talking about the rate of change of distance. So when we say this sentence in pink, we're really saying that the rate of change of John's distance, so the rate of change of f of x, is 5 times the rate of change of Mary's speed. And so this sentence corresponds to what we came up with in red. Okay? So let me record that there. And introduce other standard notations for how to say what we just said. Okay? So if you've taken calculus before, you've probably seen these, and if not, don't be afraid. It's just different standard ways of representing what we're calling the rate of change of f. Other people will denote f prime or d over dx of f, okay? Or some people will alternatively write this df dx of x, okay? But all of these should be read the same way because they all mean the rate of change of f with respect to x is 5 times the rate of change of g with respect to x. All 3 of these statements mean the same thing. Sorry, I pressed the wrong button. Okay, so, So once again, that's an introduction to other standard notations. I will continue using, well, actually, I'm going to use all 3, okay, just to help you gain familiarity with them. So try to get used to the fact that whenever you see any of these 3 representations, they all mean the same thing, which is the rate of change of the function with respect to x. Okay. So then we can generalize what we just talked about for any constant multiple. So let's say that every value of x, the function f, has a value that is c times as large as the value of g. Okay, so notice we're no longer just talking about speeds and distance anymore. Now I'm saying that the value of the function, okay, is c times as large as the value of some other function. And so you can draw the same conclusion about the rate of change, which is that at every value of x, the rate of change of f is c times the rate of change of g. Okay, and so once again, here's the mathematical statement for the given. Okay, so the value of the function f is c times as large as the value of g. Okay, and so then we can interpret the corresponding statement about rate of change of f being c times the rate of change of g using any of these forms of the notation. So rate of change of f with respect to x is c times the rate of change of g with respect to x. And the same words describe these two other versions of the notation. Okay? Now let's do another proof since we're on a roll. So in order to show mathematically, so the show it that I'm talking about is that if I'm given this situation, I want to show, for example, so let's use a different notation, that this statement is true. Okay, so under these circumstances, that implies that. So that's what we're going to prove. And so in order to do so, we need to recall that the rate of change of f, oh, I'm missing the limit again. Sorry, guys. So let's imagine taking that away. So, but we know that in order to talk about the rate of change of f, we need to think about this quotient, okay? And then because f of x equals c times g of x, I can replace f of x plus h with c times g of x plus h, and f of x with c times g of x. I can then factor out the c, and so I'm left with this expression, right? But notice that when I can sort of rearrange, and this thing in here is exactly the thing that I need to talk about the rate of change of g with respect to x, okay? So then if I think about letting h go to 0, this top expression becomes the rate of change of f with respect to x, and this bottom expression, as h goes to 0, becomes c times the rate of change of g. Okay, so let me okay. We can also come up with similar rules for adding functions. So if I define, the function k of x to be f of x plus g of x, then when I'm computing rk of x, I'm going to need to work with, I'm just going to put colons here. I'm going to need to work with this expression, right? And that is equal to, because k of x plus h would be f of x plus h plus g of x plus h, I get that here, minus f of x plus g of x. Notice when you subtract, you have to subtract the whole thing. That's a place where I see a lot of students make mistakes, is you in fact have to distribute the negative. Okay, and so what you can do once you distribute the negative is rearrange and collect the f terms and the g terms and split up the fraction, okay? And, oh, but wait, this expression, when I let h go to 0, is essentially equal to the rate of change of f with respect to x, and this expression is essentially equal to the rate of change of g with respect to x. So we established this rule, okay, which could also be written as k prime of x equals f prime of x plus g prime of x. So I said the primes, but really I should have been saying the rate of change of k with respect to x is the rate of change of f with respect to x plus the rate of change of g with respect to x. Okay. Okay. So there's the rule. And here's another way of writing it. So let me just draw your attention to the fact that I've got f plus g here because that's what k was, right? K was the function f plus g. So here's another way that we could write it. And again, this notation means the same thing. The rate of change of k with respect to x is the rate of change of f with respect to x plus the rate of change of g with respect to x. And then there's the other notation that I just mentioned. Okay? So these are exact rate of change functions, and this is the standard notation that you're going to see when you go into your textbook. Okay? So to summarize, we've established some rules for the rate of change to get the rate of change functions in closed form from these types of accumulation functions. Okay, and so these were the rules that we have now established. And so the trick is going to be for you guys to start practicing using these rules to find exact rate of change functions. So let's see how that'll look for a sample problem. Okay, and so take a second and try to do this on your own and come back and see if you follow the conversation that I'm about to have. Okay, so when I look at this polynomial is comprised of different functions. There's a function of the form x to the 11, a function of the form 5x to the 4th, another of 10x to the 3rd, and a constant function 9. Okay? And if I apply this rule, it says that if I find the derivative of the individual pieces, then adding them up or subtracting them, so we could actually add one of these in here. Challenge to yourself, figure out why I can do what I just did, and the hint is it has something to do with this one. Okay? I'm going to take the derivative of the individual pieces, okay? And so the derivative or the rate of change of p with respect to x is going to be the rate of change of x to the 11th. So rate of change of x to the 11th with respect to x. We'll go ahead and say plus the rate of change of negative 5x to the 4th with respect to x plus the rate of change of 10x cubed with respect to x plus the rate of change of 9 with respect to x. Okay? And so the rate of change of x to the 11, well, we can apply this first rule and say that is 11x to the 10th. Okay? The rate of change of negative 5x to the 4th involves this rule that I've starred and the first rule because it has both a power of x, so x to the 4th, but it's multiplied by a constant. So the third rule tells us to leave the constant, okay, so negative 5, and multiply by the derivative of the function that it's multiplying. So the derivative of x to the 4th is 4x cubed, okay? And then likewise, for the rate of change of 10x cubed with respect to x, I've got a constant times x cubed, so I'm going to leave the constant and multiply by the derivative of x cubed, okay? And then for the last term, it's the rate of change of 9 with respect to x, so I'm taking the rate of change of a constant function, and that is 0. Okay, so here we've found, so a different way that I could have written this is the rate of change of p with respect to x. And so this down here is the rate of change function for the accumulation function p. This form, notice that you could go ahead and multiply constants and simplify, but I would actually prefer that you don't, just so that I can really see your process when you take derivatives. So that's what I have for you for today. I will post an assignment on Blackboard soon so that you can have some practice with these ideas. And otherwise, have a wonderful spring break.